slowly rising through the ranks of the professorate. I'm married and have 4 children. My oldest daughter is a professor of literature in Turkey. She lives in Turkey at the moment. My oldest son runs a wine business. He sells wine to wealthy people in the United States. My youngest daughter, Charlotte, is actually here with me this week. She is studying to be, she's just finishing her master's program in speech and hearing pathology. So she was visiting Mrs. Brar's school today. That was very exciting. And my youngest son is studying to be a teacher. He's a great fan of history, and so he's finishing his master's program in history to be a school teacher. And like I said, I've been at Berkeley for over 30 years. So let's get going then on the carbon cycle and look at how carbon fits into this great world. So take a moment, will you, with your neighbor, and answer these following questions. That the Earth will eventually recover from climate change, and if so, how long will it take? And on what would that rate of recovery depend? Just take 30 seconds and talk to the person next to you about these questions, please. So I will hopefully answer these questions for you in the coming hour. No matter what we do to the Earth will continue to exist. Just may not be what it is now. How long will it take? I'll convince you it'll take 100,000 years. On what does it depend? It depends on many coupled rate processes, which I hope to get through by the end of the hour. So the carbon cycle is how we imagine carbon moves through the air, through the ground, deep into the earth and the oceans. And there's a whole myriad of processes that are associated with how carbon is moving through and around the world and the earth. And we need to understand these processes to know what is the effect of pulling carbon out of the ground, converting it to carbon dioxide, and putting it into the atmosphere. If you want to look at the Earth from a systems point of view, the way an undergraduate chemical engineer, for example, would look at it, they would see reservoirs in which 600 petagrams of carbon sit into the atmosphere, 2,000 petagrams on the surface of the Earth, oceans, deep ocean, and look at the size of this number. So, and compare it to this particular number. Most of the carbon on the planet is in the sediments and crust of the Earth. So if you want to think about it from the point of view of reservoirs, the planet Earth, the Earth part of Earth, is a huge reservoir of carbon. And near the surface, a few minor things happen relative to that very large reservoir. That's the story of today in a nutshell. Okay, let's take it apart a little bit. Carbon dioxide in the atmosphere. We think of the terrestrial as the biosphere, but of course it includes the soils. In the ocean, we have many, many carbon-containing plant life. In the deep ocean, we have these unusual and beautiful creatures. In the deeper ocean, we have shells that are buried from decaying organisms. And of course, in the sediments and crust, we have things like limestone. So this is how we're going to view carbon. And of course, the White Cliffs of Dover, as I keep mentioning, represent sort of the ultimate sequestration of carbon dioxide in the form of limestone. So I remind you that the energy states of carbon, we talked about this in my first lecture, but I just want to remind you that mineral carbonates are the most stable form of carbon, and you crawl up the energy scale as you go to carbon dioxide and then the carbon that we burn. In fact, the fact that carbon has so much energy available in the presence of oxygen is why we have the energy that we do today. So these issues all represent a balance of thermodynamics and kinetics. It's one thing to say that this is lower in energy than this. It's a whole other thing to say how long does it take to convert carbon dioxide into a carbonate. And if you think about sequestration from the point of view of ultimately capturing carbon dioxide and turning it into a rock, it's downhill in energy, but it takes a very, very long time. And it's this balance of thermodynamics and kinetics. So if we look at the exchange that happens between these reservoirs, we recognize that certainly the planet and the surface ocean and the atmosphere all represent ways in which carbon is moving around. And so we can imagine then one way to think about a mathematical model for the Earth. We could take the CO2 in the atmosphere and we say there's a rate at which CO2 is entering this box according to fossil fuel consumption, and that carbon dioxide goes into the ocean and goes into the biosphere in some form. We won't say what it is right at the moment. And so we have a rate out. CO2 is captured by these. It comes in by those. An elementary engineering student can write a differential equation for what the CO2 is in the box. They solve that equation, and it's a very simple exponential. And so we recognize then that there's a trade-off. Faster rate of fossil fuel emissions means the CO2 rises in the atmosphere, but a faster rate of absorption in the oceans and the biosphere would slower those atmospheric concentrations. So at the very last lecture at the end of the week, we're going to ask the following question. Do you believe and want to invest in, both politically, economically, and of course in terms of capital, ways in which you could bring CO2 into the oceans and the biosphere? For example, let's grow algae. Take CO2 out of the atmosphere, grow algae. Many people suggest to do that, and I hope to convince you that that's an utterly ridiculous notion. But nevertheless, these great processes, and so these simple models can be useful even to entering students in engineering. But we recognize that the CO2 levels in the reservoirs are governed by the rates that they move between them, and they're governed by the volumes of gas in those reservoirs. And so that's why I made that point earlier about most of the carbon being in the center of the Earth. That tells you that that very large reservoir is going to be very important. So for the rest of our time today, I'm going to use a mathematical tool to explain to you the carbon cycle. It's a mathematical tool that is obvious to some and completely opaque to others, and I'm not sure I can help you make it more obvious. But it's a graph. And on this axis is basically the time an event takes, or the period of an event. So, for example, this time right here would be a day, a year, thousands of years, and millions of years. And on this axis is the amplitude of some event. And so, for example, if you were to ask, what is the amplitude of toilet flushes in your apartment? And you would say that there's a peak in less than a day. And there's probably, the period is less than a day, so maybe you flush your toilet in a few hours, and that would be the period, and the amplitude would be however many flushes you have. So this variance spectrum is a very useful way to look at what CO2 is doing in the atmosphere. Here's the concentration of CO2 on a logarithmic scale in the atmosphere, and here's various events that take place that have different time scales. So here's events involving CO2 in the atmosphere that take a day, and here's events that take 10 million years. So what are those events, and how do they contribute to this? And what is the role of humankind in this variance spectrum? What is the period that we have introduced, and what is the amplitude? So let's start with this particular period. This is 10 to the minus 2 years. That's on the order of a day. That's the diurnal cycle. And what do we know about changes in CO2 in the atmosphere that happen every day? I'm sure it's obvious to all of you. This has to do with photosynthesis. That is to say, in the daytime, plants grow and they take up carbon dioxide, and in the nighttime they decay, and decomposers release carbon dioxide again, and photosynthesis again removes carbon dioxide, and decomposition releases it. You can measure it. This is a map. It's not very clear to you. It's a map of a forest in the central part of the United States, so longitude and latitude. And in the forest, scientists have placed towers. And on the tower, they've placed sensors at various heights above the floor. And they measure things like humidity and temperature and carbon dioxide. And what they can measure then, here's the concentration of CO2 at various heights at the hour of the day. So for example, here's the sunlight, and the sunlight peaks at noon, about in that part of Colorado at that time. And interestingly enough, the carbon dioxide concentration at the tree, or at the tower, is lowest, of course, because that's when the CO2 is being consumed by the plant. And then you look later at other hours, and you recognize that the CO2 is back up again because, of course, you're in that nighttime. So here's a map of this so-called diurnal cycle, and you see the change is about 10 ppm above the trees. And so we go over here and recognize then that the diurnal cycle, the atmosphere is vibrating, as it were, on a daily basis, and that vibration is on the order of a few ppm. What happens on the annual cycle? And now you probably are guessing. Remember I showed you on Monday the Keeling curve, in which we have measurements of carbon dioxide in the atmosphere as a function of time. And I said, don't pay attention to those wiggles, just look at the straight line. Now pay attention to the wiggles, please. And you recognize the carbon dioxide concentration is going up and down every year. That's easy to recognize. In the summertime, plants are growing and they consume carbon dioxide. And in the wintertime, they're dying and decaying and carbon dioxide increases. And you recognize there's a difference between the beginning of summer this year and the beginning of summer the next year. That difference is about 3 ppm. That's you and I. That's our combustion that has led to that difference. So this overall rise is characterized by this difference here. Yes, please. Excellent question. Okay, so that's a really great question. So why in the southern hemisphere it should be different? So stay with me a slide or two, and then come back and ask that question. Okay. Oh, here it is, in fact. So let's take a look at global atmospheric measurements from a variety of places, including those in the various parts of the world. In particular, I call your attention to the red versus the blue. The red represents southern hemisphere and the blue northern hemisphere. They're out of phase, as you would expect, but the more astute person in the audience would say, the blue ones are bigger than the red ones. The oscillations, and why is that? So here I've blown that up for you to see how they're exactly out of phase with each other. So the north and southern hemisphere don't mix well. It takes time to mix. Number two, there's a lot more plants in the northern hemisphere than the southern hemisphere. Okay? So that explains that particular attribute. So this swing on the yearly scale is on the order of 5 to 15 ppm. So here you have the annual cycle that represents 1 to 15 ppm. So these are two elements of the variance spectrum for carbon dioxide in the atmosphere. We'll come back to what this little thing is here in a little while. Now this is a tough one, and we're going to have to spend a few slides trying to figure this out. This is an object of great study in geological sciences. It's a fascinating thing. There are multiple peaks that are on the order of 10 to the 5th years. We know largely what they're due to, which is ocean circulation. So let me try and walk you through that for a little bit. But it's a pretty big perturbation on the order of 100 parts per million. So what happens on the order of 100,000 years? Well, you probably remember from your childhood, certainly I do and my children do, remember the ice ages. They're an object of study, the period of the dinosaurs and the woolly mammoths and all those fantastical creatures that you loved as a child. Yeah? So they're all in response to these glacial ages that happen, and that's the 100,000-year time scale that's happening. We have ice ages and then warming, and then ice ages and warming. So something is oscillating that's giving rise to that. It's the carbon dioxide in the atmosphere that's oscillating. That's the peak in the variance spectrum. And so why is that happening? So to get the data, first thing you have to do is you have to figure out how do we know what the CO2 in the atmosphere was 100,000 years ago. And geological scientists have done these amazing measurements. You probably can't see very well. The scientists here are holding these long, they look like poles. They're actually ice cores. They're cylinders of ice. So you go into the Arctic to a particular place and you drill into the ice and you pull out this core. So what has happened 100,000 years ago is it snowed in the Antarctic. And that snow fell on the ground, and embedded in the snow is the air that was characteristic of 100,000 years ago. And then another snowfall comes the next year, and then the next year, and the next year. It all gets compressed. And so as you pull these cylinders out of the ground and use a mass spectrometer and other analytical techniques to measure the composition of the gas. And you need to be clever because you have to get the timing right. So at 1.2 meters down, what year was that? And so there you have to use isotopic analyses and other sophisticated tools, and it has been done. And what you can generate then is a map as a function of year, okay, years before the present day. So this is 400,000 years ago. CO2 in the atmosphere and methane in the atmosphere, and this is an important isotope measurement that tells us a little bit about temperature. So they're obviously oscillating a lot, and that's the origin of the variance spectrum. So that's where we get the data. I saw a paper in Nature a few weeks ago in which ice core data were taken back to 1 million years, and there's a courageous effort being undertaken now by Russian scientists to get ice cores that are even more, that go back even further in time. So that's how we get the data to understand the role of the ocean. So what is it that happens here? So the ocean absorbs CO2 really by two mechanisms. One is because CO2 dissolves in water. That's how we make our soda. And the other is that organisms take up CO2 that live in the oceans, and they contribute a carbon to the ocean. Sometimes they die and then descend to the bottom. So the ice ages really are associated with the accumulation of CO2 in the oceans. And how and why does that happen, and what is the time scale? So let's take a look at oceans from the point of view of this map. Here's the air, CO2 in the air. Here's the surface of the ocean, deeper in the ocean, and then here represents the bottom of the sea floor. We'll show later that weathering processes deliver calcium carbonate, which sinks to the bottom of the ocean. CO2 dissolves in water. And by the way, if you want to challenge your chemistry students, you ask them to calculate the concentration of CO2 in the water with a given pressure of CO2 over it. If you've ever done that calculation, you know it's actually very, very tricky to do, because all of these chemical equilibria are taking place. CO2 forms bicarbonate and carbonate ions, and you release protons. And so this is where you get the acidity from CO2. If you look at how these speciate in the near surface, most of the CO2 in the water is the bicarbonate ion. And the vast majority of the Earth's crust is calcium carbonate. This happens very, very quickly. Carbon dioxide equilibrates very quickly. And this whole processes happen much more slowly, the interchange of the geological ones. So as I mentioned, ocean acidification is a measured phenomena. Here's laboratory studies that predict how marine organisms respond to less calcium carbonate. Here's a healthy organism. Here's an organism in which its shell is beginning to decompose. And here's one that's near death. And that's a 0.1 change in the pH of the water. So these organisms are extremely sensitive to pH. What happens in the deep ocean? So then you have these decaying animals. And deep down inside, you have the same equilibrium. And this equilibrium is driven by organic carbon that's dissolved, and by calcium carbonate that comes from the surface. So the organisms that die and do not decompose sink to the bottom of the ocean. That's organic carbon. And the remainder of the skeletons sink to form the deep layers of the ocean. So you have two sources of carbon. And the organic carbon gets regenerated to form this particular CO2. The calcium carbonate, which settles on the bottom of the ocean, is sort of leaving the atmosphere for good. That's a way to sequester carbon dioxide. And so we ask, how does that deep ocean carbon dioxide move around? And the answer is it moves around with the flow of waters. So these are the 5 major ocean gyres, including the Gulf Stream. And they move water only about 100 meters deep. But the amount of fluid that's moving is, as I said here, more than all the rivers of the Earth. It's really an extraordinary geophysical process. And so this forms what we call a solubility pump. And here's a map here which shows how these major ocean currents, the deep ones in blue and the surface ones in red, move water around the Earth. It's called the thermohaline circulation because it moves heat and salt in the ocean waters. And why does that happen? So you have deep, slope-moving currents that take 1,000 years to complete this whole cycle. Water evaporates from the warm, salty waters in the equators, and when that reaches the poles, it causes the remaining cold water to become more saline and more dense, and that dense cold water will upwell and move, feeding the shallow oceans with the dissolved CO2 minerals. So this is a map that shows how this works. This runs for a couple of minutes. We may not need to see it all. but it gives you a sense. These are the surface currents, and then the darker ones are the deeper currents. And these currents really have been driving the exchange of CO2 between the deep ocean and the surface ocean for many hundreds of thousands of years. The authors of this particular movie were particularly interested in the role of these currents on the climate in Northern Europe, which is why there's a little bit of time in this movie associated with those currents. Let's see if we can get to India sometime. Yes, Iceland and Greenland. So here's one of the deep currents here, surface current here. And here you have these extraordinary deep and surface currents here. South America here, surface current here, deep current here. Upwelling happens here at the poles. Here's Antarctica. So you get the idea. Okay? So the biological pump for carbon dioxide basically starts with phytoplankton. That's about half the total photosynthesis on the Earth. And these phytoplankton and foraminifera and corals, they form calcium carbonate. And this leads to a net flux of carbon to the deep ocean. They grow, they die, they go to the bottom of the ocean. They grow, they die, they go to the bottom of the ocean. And this is where this is a so-called biological pump. That biological pump happens almost exclusively in the North Atlantic. So you have nutrient from that decaying phytoplankton. It sinks and it moves along and then comes back up to the surface. But in the process, it's an efficient biological pump which takes CO2 from the atmosphere and regenerates it and leads to excess CO2, which in the southern hemisphere, the nutrient that was unused by the phytoplankton is carried into the interior ocean. There's no net sequestration. In fact, ultimately, we push up the CO2. So what you have then is northern hemisphere currents sequestering CO2 and ultimately southern hemisphere currents releasing it. And so that's the oscillation that happens. CO2 is moving back and forth and back and forth. And every time CO2 is released in the atmosphere, we get warming, we get the kind of climate we have now. When it's sequestered, we get cooling and we get the ice ages. So the role of oceans in the carbon cycles, we have a net flux of carbon from the atmosphere to the deep ocean. It's circulated around, and sequestered mainly in the northern hemisphere. CO2 builds up in the southern hemisphere, and then glaciation would interfere with this process. And so you have this coupling. It's not completely satisfying to use, I'm sure, because it's not satisfying to me that all these loops aren't completely clear. But this is the status of our understanding for the carbon cycle on this particular time scale, on the order of 10 to the 5th years. So if we attribute these phenomena to the ocean circulations, the biological pumps associated with carbon, then what is this little pump here? It's called ENSO. That's the initials. And it has to do, again, with ocean circulations. So the ocean, particularly the Pacific Ocean, is a very fickle place. It, too, undergoes an oscillation. The origins of this are not particularly clear. But if you look here, it's North America. Here's my home in San Francisco. Here's Japan over here. In this particular warm phase, you see this buildup of warm waters off the coast of the Americas. On the cold phase, the warm water has moved over here to Asia in cold water. And so this sloshing happens back and forth, and the time scale for this is somewhere between 10 and 20 years. And so here represents an index which measures the extent to which it's warm or cold as a function of time. It's a really lovely paper that was published in Nature about 1.5 years ago. And you can see regions in which we had a warm phase, and then a cold phase, and then a warm phase, and then a cold phase. And if you ask what are the consequences of that, on the planet's temperatures. And it turns out, quite interesting, that at those points where the warm water is being subducted and moved over to the North America, you're basically taking heat out of the atmosphere and putting it into the ocean. It moves to the other continent, comes up, and is released again. So you have a cycle happening. And here, what you see is the global temperature change. And you see the temperatures rising during this phase, and it's flat during this phase. That's because the heat is being taken in by the ocean, and then it's released again in this cycle. And so people have talked about, especially climate change deniers, have been talking about the fact that really since from 2010 to 2007 to 2015 or so, it was perceived that the Earth wasn't warming. But in fact, it was, because we are in one of these cold phases. And as you can probably know now, we've emerged from that cold phase into another warm phase, and the planet is heating up again rapidly. But this kind of ocean oscillation reminds us the coupling between the atmosphere and the ocean is very complicated and extremely difficult to understand. So here's another graph. Here's the global mean surface temperature. Here's the so-called oscillations. When it's warm, the temperature is rising. When it's mixed or cold, it's flat. And so we've gone through these particular cycles. So has there been a global warming hiatus? There's been a global temperature increase hiatus, not a global warming hiatus. The heat has been carried by the oceans, and it is now being released. So what about this peak right here? This is, a billion years ago. So what is the peak? What is the period? What is the time scale? What physical process takes a billion years? And the answer is this is the so-called inorganic carbon cycle, which really talks about moving atmospheric CO2 into thermodynamically stable carbonates. And it couples volcanism with geology, so that the CO2 from volcanoes, which I know you were interested in earlier, winds up being sequestered into minerals. So this inorganic carbon cycle is also coupled to the biological cycle and the carbon in the ocean. So it's an extremely complicated process. So let's take a look at that in detail here. Let's start with CO2 in the atmosphere on a rainy day. Water, of course, reacts with CO2 to form carbonates, and the carbonates weather the surface of the planet and deliver to the oceans calcium and silicate ions, because they're basically destroying rocks, and deliver them to the ocean. The silicates and the carbonates can decay or be formed into animals and then decay. So once they're decayed, you have this net accumulation of calcium carbonate in the form of shells in the seafloor, as this micrograph shows. And so when these organisms die, most of the mineral dissolves, but some of it reaches the bottom. And then if that were to happen unchecked, basically the CO2 in the atmosphere would all go away. Because eventually it winds up mineralized from this weathering process. And of course, what's the balance behind that? And the balance is that the underground is not a stable place. So you take these carbonates, they've been compressed on the seafloor. We all know about plate tectonics. The seafloor is subducted at a plate, goes into the deep earth, and in the deep earth it's hot. And what happens in that deep earth? The calcium carbonate releases CO2, reacts with silicon, and forms calcium silicate, and the CO2 comes up into the atmosphere from the volcano. So here you have this lovely geological inorganic cycle that is coupled to plate tectonics and subduction. And so now you're starting to get a sense for why these time scales are so extraordinary. As I've said here. So volcanoes emit on the order of 1/10 of a gigaton of carbon per year, and it takes about 500,000 years to replenish all the CO2 in the atmosphere and the oceans. So now we have another cycle that's associated with the Earth. It's weathering. Silicate carbonates go into the ocean, get subducted, react to form silicates. The carbon dioxide comes up in volcanoes. Here, for example, is one of my favorite volcanoes. Well, it's the only one I've ever been to. It's in the island of Hawaii. The lava gas contains a considerable amount of CO2. This particular volcano erupts more or less constantly at about 0.85 megatons of carbon per year. And the global volcanic emission rate is about 100 times that particular volcano. So now we have this lovely feedback scheme. Let's draw a box diagram and look and see how that plays out. For every increase in CO2, we get an increase in temperature, and the pH is lowered. That increases the weathering of rocks so that we're decaying silicates and delivering them silicon to the oceans. That decreases the amount of CO2 in the atmosphere. As a result of that, the temperature goes down and the pH of the surface waters goes back up. That decreases the weathering process, and then volcanoes increase the CO2 again. And we have this whole cycle going back and forth. And those of you that are mathematically inclined can write a simple differential equation for the CO2 in the atmosphere having to do with an input from volcanoes.